All right, so now let's introduce Euler's method. Which is quite possibly the simplest numerical method for the solution of an initial value problem. So as before, you start with an initial value problem. Y prime of t is equal to f of t and y of t. And t is an interval from a to b. And y at t0 is equal to y0. Okay? So we're going to assume that you have a is t0, and then there's a sort of an increasing sequence of times t0 to tn minus 1, it's like to tn, where tn is equal to the final point b. So we're trying to essentially construct an approximation of the solution over the entire time interval from a to b, where the initial value is given at the left-hand point, which is a. And then we're going to assume, if you will, that that's what I'm going to call y sub I is approximately equal to y at the corresponding time ti. Okay, and so the input basically is the differential equation, the initial data, and this sequence of times, and then the output is this vector, if you will, of or sequence of yi's, right? Okay. So I goes from 0 to n. So in practice, of course, it's very common for these time points to be equidistant, right? So it is very common for the points ti to be equidistant. Okay, so that means that ti is equal to a plus I times h, where h is equal to b minus a over n. And it's easy to convince yourself that if you had this, it's like the points, the ti's would be equidistant, and t0 would be a, and tn would be b, right? Okay, which is sort of what you want. So with that set up the way it is, it's like then we can talk about Euler's method. And I guess in principle you could have used Euler's method. It's like with these non-uniform time steps as well. It's like, but it is again very common to have this uniform time step setting. Okay, so in any case, Euler's method, right? So you start with y0 is equal to y at t0. That's the initial data which is given to you. And then that's, once you have that, you can let y of k plus 1 be equal to y at k plus h times f evaluated at tk yk. And k goes from 0 all the way up to n minus 1. And sort of the way to sort of see where that comes from is that f at tk y tk, right, is equal to y prime at tk. And y prime at tk is can be approximated by a finite difference by y at tk plus 1 minus y at tk divided by h. Okay, so if you take this approximate equality, this, it's like that this approximately is equal to this, and every time you see a y at tk, you replace it with yk, then, and you solve for yk plus 1, it's like you would then end up getting the Euler method. So that's sort of one way to think about the Euler method, is that it's coming from looking at the original differential equation and then replacing this time derivative term by a finite difference approximation of the derivative. Okay, so that's one way to think about it. Another way to think about it is using the Taylor expansion. So let's see what happens. Okay. So you can consider the Taylor series. For y of t. Okay, so let's look at y at t plus tk plus 1. Okay, so, and you Taylor expanded about the time sort of tk, right? So you get y at tk plus hy prime at tk plus h squared over 2 y double prime at some unknown point, because ck. Okay, so this is equal to y at tk plus h f at tk comma y at tk plus h squared over 2 y double prime at c. Okay, so the Taylor method, sorry, the Euler method, sort of Euler's method, right, can be obtained from sort of the Taylor series by dropping the big O of h squared term in the series. Okay, and of course, you know, this is obviously consistent with this other point of view, because if you recall, it's like deriving this sort of finite difference approximation of the derivative, it's like also involves or can be interpreted in terms of some sort of Taylor expansion and then omitting sort of higher order terms as well. Okay. All right, so anyway, so this is Euler's method, and then it's like the next thing we'll talk about are sort of, you know, what you want to do. It's like when you analyze, it's like these kind of methods. How do you measure error and things along those lines? So let me just stop here for a minute.